In this video, we'll look at our electron configurations a little more in depth and learn how we can write the quantum numbers for each of the different atoms based on its electron configuration. When we start writing our quantum numbers, we have to remember that n, that's our principal quantum number. Remember, that's the energy level that your electron is at. Then we have L. L is our angular quantum number. Remember, L shows us the shape of the orbitals. It's our subshells. So remember, N is our shells, L is our subshells. And the shapes we designated as letters. We have S, P, D, and F. And remember, each of the letters, it's associated with a number. S was 0, P was 1, D is 2, and F is 3. And then we have M sub L. Remember, M sub L was the magnetic quantum number. And if remembered, M sub L went from negative L all the way to positive L. So that means if we're looking at P, we would go from negative 1, 0, and 1. And then finally, we had our magnetic spin quantum number. Magnetic spin can either be plus 1/2 if it's going in the direction of the magnetic field. So if it's a positive, pointing up. So that was our arrows pointing up. And minus 1/2. Remember, those are when you drew our arrows pointing down. So these 4 different quantum numbers give us the exact location of each electron. And we're going to start practicing using this and figuring out the quantum numbers for each of the electrons in our atoms. And then finally, we have our N, L, X notation. And that lets us know the location of the last electron added. So it's the last electron that's added to our element. So let's start with an easy example first. Let's start with oxygen. So oxygen, we know, has 8 electrons. So let's first start by writing oxygen's electron configuration out. Remember, it's a 1s2, 2s2, 2p, 4. And so if we look at our electron configuration here, we can see the last electron we added was into the 2p orbital. So it's the 2p4. So that means if we use the NLX notation, that's going to equal 2p4 because we added the last electron was the 4th one in the 2p orbital. So now we want to look at the quantum number and figure out the quantum number for our oxygen here. It's usually a little bit easier to use the orbital diagram to figure out a quantum number. So if we look at our electrons, we have a 1s, we have a 2s, and then remember the p's, we have 3 p's. So we have 3 lines for our different p orbitals. And so with the p orbitals, we want to start assigning our m sub l's to them now so we can figure out that quantum number. Because we know with our quantum numbers for oxygen, n equals 2, because it's the 2p that starts to get filled. So I'm using the n level. And since it's p, remember for our l's, P equals 1. So that'd be 1. So M sub L, that's our next letter we want to figure out, our next quantum number. So when we're figuring out the M sub L quantum number, we have a 0. And then remember, our L went to 1. So we're going to write a -1 and a +1. So that way we go from -L all the way to +L. So now we want to figure out where that fourth electron got put in which of these M sub L's. So remember, when we're filling up our orbitals, we fill up from lowest to highest, and then we follow Hund's rule and we fill across. So I've done 3 electrons, and then the fourth one, this electron, you can see it went into the -1. So our M sub L is -1. And then finally, we want to look at our last quantum number, M sub S. That last electron, did I put it pointing up or down? Since I put it pointing down, M sub S is actually a -1/2. So the quantum numbers for oxygen are 2, 1, -1, and -1/2. Since that's the location where I put the last electron into oxygen. And then finally, if we want to take a step further, is this paramagnetic or diamagnetic? Since I have 2 unpaired electrons, it's paramagnetic. See, not so bad. And now let's look at another example and do another example of this. So I'd recommend getting your periodic tables if you don't have them already. So now let's try another example. Let's look at the electron configuration for arsenic. Arsenic, we know, has 33 electrons. So now I want you guys to try and write the full configuration and the condensed configuration on your own before looking at the answer in the video. So the full configuration for arsenic, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then finally 4p3, which means our condensed configuration is where all of this equals argon. So it's argon, 4s2, 3d10, 4p3. So now that we know its configuration, what is its NLX? So remember, the NLX tells us where we put that last electron. So that happens to be 4p3. So its NLX is 4p3. Now we want to figure out its quantum numbers. We're going to look at that 4p3 orbital. That's the last one we put in. So remember, your p orbitals, we have 3 p orbitals. They go from -1, 0, +1. So now when we add those electrons to those orbitals, remember Hund's rule, we go across, so we got 1, 2, 3. So I added the third electron. It ended up in that +1. So that means the quantum numbers for arsenic are your N is 4, your L, since we're in the P, L has to be 1. We ended up in the +1, so that's another 1. And then since the electron's pointing up, that becomes a +1/2. Or we can just write 1/2. So now we have our quantum numbers for arsenic. And then finally, is this paramagnetic or diamagnetic? Since those electrons are unpaired, we have a paramagnetic element here. So now let's try one more. Let's try something a little bit harder. Let's look at iridium. Iridium is element 77. So that means there's 77 electrons. For this one, let's skip the full configuration and just write the shorthand notation. So for iridium, we have xenon, and then it's 6s2, 4f14, 5d7. So this means the last electrons we put in were in the 5d7 orbital. So that's our NLX, 5d7. So now when we want to figure out all the quantum numbers for that, and we draw the orbitals for the d, remember we have 5 orbitals in our d subshell. And then those we start 0, -1, -2, +1, +2. So when I'm filling it up, 1, 2, 3, 4, 5, 6, 7. So that's our last electron. So when I write the quantum numbers, we're in the n equals 5. Since we're in D, our L is now going to be 2. And then our M sub L, that's -1, since that's the last electron. Where we put that was in the -1. And then since it's pointing down, it's a -1/2 for its spin. So now the quantum numbers for iridium are 5, 2, -1, -1/2. And then finally, since we have 3 unpaired electrons, it's paramagnetic. And then finally, our last example. Let's look at plutonium. Plutonium is element 94, which means now we're looking in the lantanides and actinides series. We're looking in those rare earth metals. So again, if we start with its condensed configuration, it's radon, 7s2, 5f6. So that 5f6, that's the last location of our electrons. So now when we want to draw the orbitals out for the F subshell, remember there's 7 of them. So if you remember F, its L number is 3. So if we look at L, remember S, P, D, F, that was 0, 1, 2, 3. So we have to go from -3 all the way to +3. So now when we're filling that up, we start filling across. 1, 2, 3, 4, 5, 6. So there's our last electron that we added, was in the +2. So that means its quantum numbers are going to be 5, because we're in the 5f. Remember, f is 3. We stopped at the +2 for the m sub L. And our electron's pointing up. So it's a +1/2. And then we can also see here we have 6 unpaired electrons. 6 unpaired electrons means paramagnetic. And if you write the NLX notation, which we forgot to do, that's going to be 5f6. to write out the numbers for any given element and write out the NLX notation. So anytime I give you an element, you should be able to write the full configuration, condensed configuration, quantum number, NLX, and tell me if it's paramagnetic or diamagnetic.